now let's test our understanding. All right, so these momentum square diagrams, you're not going to be asked about these in any way, but they are really useful in understanding where momentum is, where it goes, and what it is. So we have a 2 kilogram toy car. We have our mass on the x-axis and velocity on the y-axis. So we would say 2 kilograms because mass is measured in kilograms. 2 kilograms, and then it goes 3 meters per second, so all the way up here. And you could just shade in these blocks, and that would be your momentum for this object. Here we have a 4 kilogram moving to the left at 2 meters per second. Left means we have a negative velocity, so we would shade in these blocks. 0.1 kilogram travels upward at 400 meters per second. Our velocity is in 100 meters per second, and the mass is in 0.1 kilograms. So 0.1 kilogram, 400 meters per second. Reminds me of being in like first grade, kindergarten, something like that. When you first started adding and you had these little blocks that you stacked up, the unit blocks. A 2,000 kilogram car moves at 30 meters per second to the west. West we take to be negative 2,000 kilograms, 30 meters per second. And that's it. State the definition of impulse. Impulse is your change in momentum. Using J, you might use I, either one, capital J, I. State the definition of impulse. Impulse is just the change of momentum. It is also force times the change in time. So, momentum, remember, kilogram times meters per second is the unit. And over here, we have a Newton times a second. What is a Newton? A Newton is mass times acceleration, so it's going to be a kilogram times meter per second squared acceleration times a second. And look at that. Seconds cancel out, and we're left again with kilograms times meters per second. How is impulse due to a constant force calculated? Impulse due to a constant force calculated, we would just do the change in momentum equals F delta T. So that's a constant force. So our force is not changing. If our force is changing throughout a situation, then we would need to graph this, F versus T. And when we graph F versus T, do you remember what the slope is of F versus T? If you do, you'll have to remind me because I don't know what F divided by T is. That doesn't make any sense to me. Instead, what I do know is F times my change in time. Let's say we have a force that does this, and we wanted to find to this point right here. We would just find the area under the curve. So when you find the area under the curve, you are multiplying your y-axis by your x-axis. So area under the curve for force versus time. Okay? All right, so the impulse momentum theorem is, impulse is the change in momentum. Impulse equals change in momentum. That's what it is. So that means F delta T equals M VF minus M V naught. Final minus initial. That's what that delta represents. We can't change our mass. The only thing we can change is the velocity. So it's final minus initial. What law of physics is the impulse momentum the same as? Well, I'm going to rewrite it here. So F delta T equals mass times change in velocity. That's the same thing as change in momentum, right? That's math, just pulling out the m, right? All right, so if we divide delta t from each side, what's happening here? That goes away. We get F equals m delta v over delta t. Okay. Oh, wait a second. Look at this. What does this mean? F equals m delta v over delta t? What? Yes. Impulse momentum theorem. Same thing as Newton's second law. Newton's second law tells us acceleration is directly proportional to the net force and inversely proportional to an object's mass. So this version right here, m times delta v, it could be F equals delta p over delta t, right? And this is actually how Isaac Newton used his formula in his book, Principia. Let me see, what do I have to grab here now? We're going to now start with the definition of acceleration and the relationship between acceleration established by Newton's second law. This is exactly what I just did. Let's see. Here, this is the derivation of the impulse momentum theorem. And remember what deriving an equation means. It just means showing the steps that happened. So we have to first find a starting point. And the starting point that we're given is this. A equals the change in velocity over the change in time, and A equals F net over m. So what did we do here? Explain this step in words. We set A equal to A. Okay? So all of this stuff equaled A, all of this equaled A, and we just set them equal to each other. That's allowed and expected that you are comfortable with that. Then what did we do? How did we go from here to here? All we did was multiply m on each side. When we multiply m on this side, the m will go away. When we multiply it over here, we get m times vf minus vi. And then we multiplied by delta t on each side, final time minus the initial time. When we did that, our denominator went away on the left side, and then it gets multiplied by force. So how did we go from step 3 to step 4? The left side is the final momentum minus the initial momentum, or delta p, and the right side is force, the net force, times final time minus the initial time, which is just delta t.